Hello everyone, good day. My name is Handre. Today I will present our research in battery system. Our research is development of digital twin platform for electric vehicle battery system. As we know, electric vehicle demand has been increasing over the years. One critical component of this battery system is it require a battery management system to monitor and control the operation of the electric vehicle. Also, deliver the safe and reliable function of the battery system. One of the challenge is monitoring the battery state require massive storage space and computation power, especially at this very large scale of battery system. One solution is to apply digital twin concept that can provide solution for those challenges. The digital twin or DT is the digital counterpart of a physical entity. It can be an object or a process in a virtual space. Characteristic of this digital twin is high fidelity models that mimic the state of the physical entity. What differentiates this digital twin with a digital model? A digital model is only a snapshot, the physical object at time, while a digital twin, it continuously provide the current state of the physical space system or the actual object or process. In order to build a digital twin, we require five dimensions: physical, virtual, connection, data, and service. In our research, we focus on the data side because it requires massive data from sensor to process and to build the model for digital twin. In a previous research of this kind of digital twin, only a few have mentioning about data pipeline. Well, this data pipeline is a crucial part to make sure to provide real-time data to build a digital twin in the virtual space. So our research contribution is the digital twin platform that include data pipeline and modeling tools. We develop our digital twin platform on application platform called CDAP. It's application platform for building and managing data application. So here's our structure for a digital twin platform. It include data lake, data warehouse, and data visualization. Data lake, data warehouse, and data visualization were built on top of a server on premises with the configuration as shown in the figure. While the data source is an embedded system that embedded in electric vehicle to gather all the data from sensor in the vicinity and continuously send the written data to the data lake. The data lake on the other side is a virtual machine. It pulls the data and store it in the form of a packet. Then it utilizes a battery model in a neural network model that built on neural network to estimate battery state of charge. After the data lake estimate the SOC or SOC or state of charge, then it send the SOC to estimate then it send the SOC estimate to the data warehouse. Well, the data warehouse will store the data, the operation data to be visualized in data visualization. For testing the develop that digital twin that we have developed, we use the performance measurement framework for cloud computing. It's adapted from the ISO standard. It includes the service done for functional test. In our case, is SOC estimation. So the platform needs to perform the service correctly and without any anomalies, which include null values or duplicates. For the second set of tests, we do the performance efficiency or performance test that include time behavior, execution time, and resource utilization that include processing time and memory. Sorry, processing power and memory. For the last, we also measure the capacity or data size that can be processed in our digital twin platform. For the functional test, result of the functional test, data can flow throughout the pipeline from the data lake to the data warehouse. Can be shown in figure. We show that data. We show the SQL database in data warehouse. So the voltage, temperature, and state of charge of the battery system. The platform successfully carry out the task of estimating the current battery state of charge, as can be shown in the figure. Because of data lake already clean the null values, so in the data warehouse there were no null values. And also we have assigned a unique ID for its measurement to avoid duplication. As you can see in the figure, there are no null values and any duplication. Here also we present the data visualization or human machine interface of our battery system. For the performance test, we configure the data lake into two configuration. Configuration 1 and configuration 2 with a different virtual CPU and RAM. And we test the platform with different data lake configuration with different data size, 1,000 until 1 million row in packet format. Or in data sizes, it's 6.2 until 4,900 kilobyte data. So here's the result of configuration 1 and configuration 2. We can see that configuration 2 execute the task slightly faster than configuration 1 at small data size. And for a bigger data size, the configuration 1 outperformed configuration 2. The configuration 1 clearly have better resources. We also monitor the utilization both of CPU and RAM for its virtual machine, its configuration for the data lake. We investigate further for configuration 2. RAM usage for configuration 2 nearly maximum, can shown here at the data size of 4,900 kilobyte. So from this result, it may be the RAM or the memory can cause a bottleneck for configuration 2. Well, we can see that it still have enough computation power, but the RAM is nearly at maximum. So we do another test, the second and the third test. The second test is for the memory size. So we configure the data lake with the same virtual CPU, but different memory sizes. So here's the result. Clearly show that the performance of digital twin platform affected by memory size availability. As we increase the memory size, the execution time can be reduced. Also show a strong correlation with R square 0.99. There is the exponential relation, so it means that there are an optimum number size of time that we can go through. So at some point, adding more memory size will only slightly reduce the execution time. For the third test, we configure the data lake with different virtual processing power, but the same memory sizes. The results show that adding more computation power can also reduce the execution times. It's more rapid adding computation power than memory sizes. The translation is still quite strong, 0.60, 0.76, although it's not as strong as the previous result. So we can take a conclusion from this, from both of these results, that upsizing the computation power make task execution faster than we expanding the memory sizes. So here's our result summary for a different configuration. So if we doubling the CPU, then we can reduce execution time 11.9%. If we quadrupling the RAM sizes, we can reduce execution time by 9.9%. If we do both of doubling and quadrupling the CPU and RAM, we can reduce the execution time 12.3%. So doubling the CPU reduce computation more than quadrupling the RAM sizes. And data lake with same number of cores, but with different memory size, only slightly better. So it means that the platform performance is affected more by computation power rather than memory sizes. So our conclusion, the result of performance test suggests that SOC estimation is a computation intensive process. As neural network we use in SOC estimation, it was heavily repeating calculation. Another way to improve the execution time is parallel computing via GPU. And also an adequate amount of memory sizes is also necessary to ensure optimal computation time or reduce execution time, as we shown in our test result. So we only managed to collect 4 data points for the CPU variation test. We show previously. In the next research, we will do more rigorous data to have a better R square value. We will continue our test with different variation to get more data points and also adding GPU as the test variable. That's all for today. Thank you.